So last time we were working with a gigantic new kinematics equation. I mean, we have the basic dTV, you've got the basic, VAT, which never go away, and then I should introduce you to the big mother equation of kinematics, the d2 equals d1 plus v1t plus 1f at squared, which looks like a huge formula. But remember, a lot of the times parts just disappear. v1's equal to 0, acceleration's equal to 0, d1's almost always equal to 0. You just use whatever parts that are actually left over. Now, the only thing is, all three of these expressions, especially the big one, they're very, very, very reliant on time. They all have t. If you don't have t, these expressions just do not work. You're sort of stuck. So what we're going to do is we're going to do another derivation type thing with little expressions and see if we can have a different expression which doesn't rely on time, because time it's just too difficult to always have. So I'm going to go back to the two simple expressions. Remember, we built that big one based on the two little guys. We're going to do the same thing again. I'm going to take those little guys and use them in order to create another expression that doesn't rely on time. So I'm trying to get rid of it. So if I take both of these guys and I solve for time on both of them, I get these two. And if I just equate those two expressions together, they will then cancel out t. So if I just, equate the two, and I can do that no problem, d over average v is going to be equal to delta v divided by a. And right there, I now have an expression with no time. I've got distance, I've got acceleration, I've got v's, but no t's. Now, we're going to use this, we're going to manipulate this a little bit and get the more common expression that's typically seen. Now, the first thing I'm going to do is I'm going to flatten this thing out. Fractions generally suck. So I'm going to cross multiply. So I'm going to just take this and move it over here. I'm going to cross multiply. And if I cross multiply, it would be the delta v times average v is going to be equal to a times d, something like that. And now we're going to do some more like that substitution type stuff to sort of clean this up a little bit. The a and the d are fine. We're not really going to do much with any of that. But the change in v and the average v, those are kind of ugly. You don't typically know the change in v or the average v. It's usually something you solve for. You often know v1 or v2 and use them to find those two. So let's put these guys into terms of what you more typically have. So if I would take my change in v, a really common way to find change in v is just to subtract v2 and v1. So I'm going to use that and substitute that in there. For average v, a really common way you guys have found average v is just add up the two v's, add them up, divide by 2, and I'm going to put that in there. And as soon as I do that, I'll have this in terms of v1 and v2, which is much more commonly known. And sometimes one of them is just equal to 0, which makes it even easier. So let's substitute those in there and then see what we can work with. So this is going to turn into v2 minus v1. This is going to turn into v1 plus v2 divided by 2 is equal to a times d. I'm just going to drop the brackets on the right-hand side. Now this looks kind of ugly and disgusting, but we're going to clean this up a little bit and not worry about it. One of the simplest things I'm going to do is I'm going to move the 2 to the right-hand side. I'm going to multiply both sides by 2. And if I do that, I'll have v2 minus v1, and then that 2 is gone, and I'll be left with 2ad on the right-hand side. Okay. Now, I've got the two brackets, I got the two v's. Now, if you look at this carefully, especially if you sort of flip the two v's in the second set of brackets, hopefully you'll sort of recognize what that is from math class. You've got two variables, and one time you're adding them, and the other time you're subtracting them. And there's no exponents or anything like that, or anything weird, no coefficients. You've just got a subtraction and an addition, and you're multiplying the brackets together. And hopefully you can recognize this. This is actually a difference of squares. So if you'd multiply this out, the middle terms cancel out, you are going to be left with v2 squared minus v1 squared. It's a difference of squares. Okay? So if I use that idea, this would then be equal to this. We'd have v2 squared is equal to v, not equals, get rid of that, minus v1 squared equal to ad. Now I'm going to add, get rid of the subtraction v1 squared. I'm going to, people often like things all positive. And I'm just going to bump this to the other side, and we're left with oh, not equals, but that should be a plus. Let's clean that up. Something looks like this, which is a nice expression. We've got V's, we've got A, we've got D, we've got the V's in terms of more common V's to know. And again, if V1 is equal to 0, this term disappears. It's fantastic. But no time. We do not need time to solve for any of the values we might actually want. So the same way this big expression is great to make things a little quicker, more accurate, more consistent, and more encompassing all the ideas put together. Same thing for this one, where you're actually able to calculate things more efficiently, quickly. Often parts, especially V1, is often equal to 0, often starting at rest. It's just a quicker, more efficient way to actually do it. And the big difference between the two is time. If you've got time, you're probably looking at one of those three. If you don't have time, time's not mentioned, you're not looking for time, then you're probably going to work with this guy over here. Okay, and you'll often see in chemistry, not chemistry, well, sometimes chemistry, but mostly in physics books, you'll often see they'll have like DTV, they'll have VAT, they'll have the big one that we did last time, and they'll have this one listed as V kinematic equations. And sometimes there's also they'll also sometimes have this one as well. There's like 4 or 5, sometimes 6 different versions that you'll see, and they're the kinematic equations. And basically with DTV, VAT, this one here, and the one we just derived, between those 4, there pretty much isn't anything you can't actually solve for. They work really well. And sometimes one type of equation is more beneficial than the other, but they all work out really, really, really well. Okay, and again, time's the thing. No time mentioned, you're probably using the new one. Other than that, you're probably relying on the first ones, but they all go back and forth. So let's practice with this new one a little bit, and I can sort of show you how it works. All right, so let's do something really, really simple. Okay, here we're going to have a guy going for a run. Let's even give him like a cool, like a head sweatband type thing. There you go. He's going for a little run. And let's say here he is running at 1.6 meters per second. And he runs along. And let's say over here, let's say he's gone, let's just say he's gone 4 meters. And over here, he is going 3.8 meters per second. And I want to know what was his acceleration. Now, you could have done this last year. Now, if you'd done this last year, what you'd have done is you'd use those 2 V's to find out the average V. Then you use the average V in the distance in order to find the time. Then you would have found the change in V, and then use the change in V in the time to get the acceleration. There's 4 steps there. Now you can do it all in one. You've got the first V, the final V, the D, you're looking for the acceleration. No time mentioned anywhere, so pretty much guaranteed I want to use that expression we just derived. So if I do V2 squared is equal to V1 squared plus 2AD, and do a little checklist here, well, there's my V1, there's my V2, there's my D. Acceleration is the only thing I don't have, so I can solve for it. So acceleration would be V2 squared minus V1 squared divided by 2D. I just have to put in the values and I can find the acceleration. And hopefully get around 1.5 meters per second squared. Okay, so that's how this expression can be used. Works really, really, really nicely. Okay, let's try something else. Let's go here. Let's draw. Okay, we'll draw a car. Nice, fancy green car motoring along, and let's say the car is cruising along at, well, let's go with 18 meters per second. Okay, and then up here, there is a different speed zone over here, and I don't know why, but the thing's in meters per second, so let's say it's the speed limit here is 6 meters per second. And what we're going to do is we're going to have this guy sort of slow down in time. And let's say he slows. He's going to slow down. Let's say he slows down at Let's go with 2.4 meters per second squared. So how far did he go? Okay, so again, no time mentioned. We're just practicing with the new expression anyway, so let's do that. So v2 squared equals v1 squared plus 2ad, and in this case, I am looking for the distance. And, you know, if you want to put in the v's and get the numbers and do it that way, that's fine, especially when you're starting out, but you want to sort of get in the practice of actually rearranging these things. So I would subtract the v1 squared from both sides, and then I'll divide by 2a, okay? And we'll sort of piece this all together. Now, if we do the v squareds, okay, actually, oops, that should be an a, not a d. Fix that. There you go, that's better. So if we do that, if I do the v2 squared minus v1 squared, so I've got the 6 squared, I'm going to subtract that from the 18 squared. That gives me negative 288. Now the negative might throw you off a little bit, but that's okay because since the car is slowing down, that is a negative acceleration. And just like you got to be careful with the other expression with negatives if you're slowing down, same thing for this one. This value here, that acceleration is also going to be negative, and the negatives will end up canceling out, which is exactly what we want. So we've got the negative 288, and we'll divide that by negative, well, 2 times 2.4 is 4.8. See, the negatives will cancel out. So we'll divide 288 divided by the 4.8, and we're looking at around 60 meters. Okay, so again, just be careful of the negatives. Often with the DTV, VAT, we would just drop the negatives to incorporate afterwards. These new expressions, sometimes you just got to be a little bit careful about the negatives in terms of, you know, with negative accelerations, slowing down, point of reference, that type of stuff. Okay, all right, let's do some more practice with this expression. So let's do a question actually similar to what we had. I think in the last video we had a question like with a tree or something like that, and something falling out of a tree. So I'm going to draw a tree, blah, 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 something like that. Get some leaves on there. I don't know, let's say there was a cat. There you go, a cat that was in the tree. All right, and the little cat just jumps from the tree and just goes down, something like this. And let's say, I don't know how high cats go in trees typically, but let's say it was 6.4 meters in the tree. So I want to know how fast is it going when it hits the ground. Okay, so again, I'm just going to use the new expression because that's what we're practicing right now. And v2 squared is equal to v1 squared plus 2ad. Now, this one's nice because my v1 is equal to 0, so I can actually just get rid of that term altogether. So v2 squared is going to be equal to 2ad. Now, the distance is 6.4. This right here, of course, is gravity, which is 9.81. And of course, you might think, hey, it's negative 9.1 because it's going down. Well, you can actually sort of make it positive negative depending on your frame of reference and your point of view and that type of stuff. And if I put negative 9.1 in for gravity because it's going down, I try and square root this later. Square rooting a negative doesn't work out very well. So you can look at a different perspective. The cat is being sped up on the way down, so I'm just going to leave it as positive 9.81. So this would be 2 times 9.81 times 6.4. So I can multiply those all together. And if I multiply the 2 times 9.81 times the 6.4, I get a value. Don't forget to square root it. And if we square root the product of those three things put together, we'll get around 11.2 meters per second for the speed of the cat. Okay, so again, there's more practice using the new expression. Again, with this one and the previous ones, you can solve for lots of different things. There's no necessarily rules which ones you have to use where. Some just work better than others in different circumstances. It all depends on the situation, the information you're given, how you see the problem, how you see the question, how many steps you want to do. People go back and forth between them, but it's a great expression. If you don't have time, you don't want to use time, you don't want to find time, this expression works really, really, really well. And when you have just general kinematics questions, you're not sure which one to use, well, you just look at the information you're given, and time is the big key. Okay, and if you don't have time, it's a good idea to give this expression, this equation a try.